when you see a heavy-duty cement mixer pull onto a construction site, you see this icon of raw power, right? But what you're actually looking at is a marvel of incredibly complex, synchronized control.
It really is.
And today, we are going to tear apart the blueprint, this professional consultancy document that lays out exactly how an engineering team can build complete tuning capability for what might be one of the toughest systems out there.
We're talking about the P2 hybrid cement mixer truck. And it's a genuinely immense engineering task. You're mashing three completely different, very complex domains together. You have internal combustion, you have a high voltage 400-volt electric drivetrain, and then you have the heavy-duty liquid handling system, which is the concrete drum itself.
Okay, so let's unpack that. Our mission for this deep dive is to build out the entire capability stack for the system control unit, the SCU calibration. And this isn't just, a list of parameters. It's a whole systematic approach.
It has to be.
It covers power optimization, getting the best fuel economy, making sure the driver's comfortable on these chaotic job sites, and maybe most importantly, meeting those non-negotiable functional safety standards of ISO 26262. We're building the entire control software house from the foundation up.
Precisely. And the challenge is huge, but the blueprint, it organizes this whole task into 5 foundational pillars. These are, the mandatory phases for successful calibration engineering. If you miss one, the whole thing just collapses.
Okay, so lay them out for us. This will be the map for our deep dive.
Right. So first we have protocols and environment. That's all about setting up the foundational data contract and the high-speed communication you need.
Okay.
Second is tooling mastery. This is about enforcing a really disciplined use of calibration software, things like INCA and CANape.
Right, the actual tools of the trade.
Exactly. Third, we hit core control, PID, and that's the pure physics problem, tuning that incredibly nonlinear drum load. Fourth is vehicle strategy, which is all about drivability and making that hybrid coordination feel seamless.
And the last one.
And finally, validation and safety. That's the rigorous process you have to go through to get ready for mass production, or what we call SOP.
That roadmap really shows just how complex this is. But if you had to boil it all down to one single central difficulty, what's the biggest engineering headache that the SCU actually has to solve here?
It's the sheer dissonance between the systems. I mean, you have these massive, high inertia, really sluggish physical systems that tons heavy spinning drum full of concrete.
Right.
And you have to coordinate that with millisecond level electrical responsiveness from the 400-volt motor, especially when the hybrid system is switching modes.
So you're trying to harmonize this slow mechanical reality with instantaneous electrical power.
That's it. And if you fail to manage that, you get driveline shunt, you get poor concrete quality because the mixing is unstable, or, worst case, you have a serious safety incident.
So if the challenge is coordination down to the millisecond, then that first pillar protocols, it has to be all about the quality and the speed of the data flow. If the engineers can't see what's happening fast enough, they can't possibly tune it.
Absolutely. The modern hybrid control strategy, it generates an extremely high signal density. We're monitoring, continuous torque paths, instantaneous energy flow, hydraulic pressures, the position and speed of mechanical parts. We need to observe literally hundreds of variables at the same time.
And at high speed.
Often requiring 1 millisecond resolution just to accurately capture that transient behavior.
So why does the communication standard that's, served the auto industry for decades, traditional CAN, why does it just completely fall short here?
Well, traditional CAN 2.0b has 2 fundamental limitations that just make it unusable for this level of high-speed calibration. First, the speed limit. 500 kilobits per second.
Okay.
You hit maximum bus load almost instantly, just logging the core VCU parameters. But the second one is the payload constraint. Only 8 bytes per frame.
Only 8 bytes. That's nothing when you're talking about this much data.
Exactly. If you're trying to capture the exact moment the clutch engages and disengages, or the torque overshoot that results from it, that 8-byte limit forces you to send critical signals in separate delayed messages. You lose the context.
And when you miss those transient peaks, that single millisecond of maximum jerk, your entire calibration is basically built on a false premise. You're tuning something that isn't real.
Precisely. The dropped frames, the excessive bus latency, it all misleads the calibration process. So the solution, which the blueprint mandates, is the shift to the high-speed standard, CAN FD, or flexible data rate.
Okay, so what's the leap in capability that CAN FD gives you? What problem does it solve?
It gives you 2 critical upgrades. First, speed. It dramatically increases the data segment rate. You're pushing it up to 2, sometimes even 4 megabits per second.
Wow.
And second, and this is arguably even more important for these complex systems, it extends the payload from 8 bytes to 64 bytes.
8 times the data in a single frame.
Right. Which means you can pack all your related variables together, you can observe them synchronously within that crucial 1 millisecond window, and you significantly reduce the overall bus load.
That increase in throughput gives the engineers the granularity they need. The blueprint calls these required logging speeds rasters. So what are the specific timing targets here? How do you differentiate the critical signals from the standard ones?
We establish 3 tiers. For the absolute fastest, most critical closed loop, so we're talking about the current and speed control inside the motor loop, we mandate a 1 millisecond raster.
1 millisecond.
This is absolutely essential for the PID tuning we'll talk about later. Next, for the systems that manage larger, slower operations like the vehicle control unit deciding on hybrid mode shifts or energy regeneration, a 10 millisecond raster is required. This governs drivability and energy management.
Okay, that makes sense.
And finally, for just status monitoring, things like thermal management, battery state of health, or onboard diagnostics, that's acceptable at a 100 millisecond raster.
So the VCU logic deciding when to shift modes can wait 10 milliseconds, but the E-motor executing that torque command has to be verified 10 times faster at 1 millisecond.
Exactly.
Okay, that makes perfect sense. Now, let's get physical for a second. This is a heavy-duty truck. What kind of hellish environment is this data highway actually running through?
It's a severe electromagnetic interference, or EMI, environment. I mean, you've got high-voltage 400-volt harnesses, often meters long, running right alongside your CAN harnesses.
Not ideal.
Not at all. When that 400-volt motor is switching current, it generates enormous electrical noise. And since CAN FD operates at these higher frequencies, it becomes acutely sensitive to physical layer defects like impedance mismatch or signal reflections.
So this is where the really strict rules on physical wiring integrity come in. The blueprint cites ISO 1118-98-2. What are the non-negotiable physical rules?
Okay, first one is mandatory impedance matching. You have to place 120 ohm termination resistors at both ends of the bus. You must have that clean termination.
At both ends.
At both ends. Second, and this is where calibration engineers often clash with the vehicle wire installers, is the management of branch lines, or stubs.
That detail about the stub length, I feel like that's something that often gets overlooked until there's a problem. Why is it so critical to limit any branch line off the main bus to less than 0.3 meters, so 30 centimeters?
Because a stub acts like a tiny antenna, and it creates a signal reflection point. We call it a ringing effect. At the megabit speeds of CAN FD, that reflected signal can interfere with the primary signal just as the receiver is trying to sample the data.
So a wire that's a few inches too long could ruin weeks of software tuning.
Absolutely. If your installer used a 40 or 50 centimeter stub just because it was convenient, you might spend weeks diagnosing intermittent data loss, only to find the problem wasn't the software at all, but a simple wiring flaw. Limiting that stub length is fundamental.
It's a prime example of a hardware constraint dictating the success of software calibration. And that leads to the timing of the data acquisition itself, right? The sampling point precision.
Exactly. In traditional slower CAN, sampling late, say at 87.5%, was usually fine. But in the long harness environment of a heavy vehicle running at high frequency, we need a precise adaptation. The recommended engineering practice is to set the data segment sampling point between 75% and 80%. We actually move the sampling point earlier.
And why the earlier sample time? What are you trying to avoid?
It's a calculated compromise. We move it earlier to mitigate the risk of that high-frequency interference, that ringing effect we just discussed, which tends to manifest later in the bit time. So this balances that interference risk against the inevitable risk of clock drift over the extremely long, noisy wire runs you find in these trucks. It's an optimization point for the physical environment.
So we've built the highway. Now let's talk about the traffic rules and the manifest for the data traveling on it, what the blueprint calls the contract, the A2L file.
The A2L, or ASAM ASAP2 file, is the absolute foundation of trust. It's defined as the only contract between the ECU software and the calibration tools like INCA or CANape. If that file is incorrect, everything you see, everything you log or adjust in your tool is suspect.
You might think you're adjusting the engine's idle speed.
But you could actually be writing to a completely unrelated, safety-critical memory address.
And that potential for a silent failure, From a functional safety perspective, that sounds terrifying.
It is the ultimate nightmare, and that's why the blueprint enforces this core principle. An unaudited A2L is not allowed for real vehicle calibration. The engineering red lines are absolute. Manual modification of A2L memory addresses outside of the authorized toolchain is forbidden. Period.
You can't mix and match versions.
Never. The A2L must perfectly match the compiled HEX file version. If the contract doesn't match the code, you are violating the entire functional safety assumption.
Let's clarify the taxonomy inside this contract. When an engineer opens up the A2L file, they see terms like characteristic and measurement. What's the fundamental practical difference between those two?
Okay, so a characteristic is a parameter the engineer is authorized to change. These are the tunable assets, the maps, the curves, the single values that govern control. PID gains, torque limits, shift schedules.
The things you actually tune?
The things you tune. A measurement, by contrast, is purely an observation signal. Engine speed, pedal position, battery current. It's for logging and display only. You look, you don't touch.
And the blueprint has a really strong rule about how you can use these two categories.
No. It does. It strictly forbids using a measurement as the basis for a closed-loop adjustment in the ECU software. You cannot write control logic that says, if measurement X is greater than 50, then do Y.
Why is that rule so severe? Why can't the ECU trust its own measurement signals?
It all comes down to latency and signal processing. The value you read as a measurement in your tool, it might have gone through filtering, averaging, communication buffers.
Yeah.
It could be several milliseconds behind the actual physical reality.
So it's stale data.
It's stale data. And basing a real-time closed-loop decision on stale, slightly lagged data is a guarantee for instability or, dangerous miscalculation. The ECU has to use its internal high-speed signals for control. Those are often defined in the software itself, not exposed as these external measurement signals that we use for calibration viewing.
Okay, last thing on this. ASASPTS, the coordinate axes. This is a subtle point, but the blueprint suggests they're more than just, mass coordinates on a graph.
Oh, they are critical. An AXISPTS defines the boundaries of the control map. So if you have a map indexed by engine speed, the defined axis point 0 RPM, 500 RPM, 1000 RPM, and so on, they determine the working application boundaries of the entire control strategy.
So changing them is a big deal.
A huge deal. The blueprint emphasizes that if you modify an AXISPTS, you are fundamentally redefining the strategy's operational range and its resolution. It's a much, much deeper change than just adjusting a value within the map, and it requires maximum scrutiny.
So we have a clean, high-speed data contract. Now we move from the rules of the road to the actual vehicles we drive on it, the calibration tools. The second pillar is tooling mastery, which sounds like it emphasizes discipline over, personal preference.
This transition is really where amateur tuning ends and professional engineering begins. There's a famous mentor's warning here. 90% of calibration confusion starts with a haphazard workspace structure.
I could believe that.
When you have multiple engineers working on a shared vehicle fleet, data corruption and history loss they're guaranteed if you don't have a strict structure.
So what kind of standardized INCA workspace architecture do you implement to prevent that chaos and ensure you can trace everything back?
We implement a rigidly standardized architecture. Every single engineer accesses the exact same file structure. We need separate dedicated folders for 01, A2, LHEX release. Those are the audited source code contract files. You import them as read-only.
Okay.
Then O2 experiment for the logging configurations, 03 measurement data for the raw, timestamped log files, and O4 calibration data. That's where the actual tuning files, the DCMs and PRs live.
So that separation means a mistake in one folder can't accidentally contaminate your critical source files or overwrite essential raw data.
Exactly. It's about containment and clarity.
And inside that folder structure, how do you handle versioning and managing the INCA projects themselves?
Projects have to be strictly linked to a single, unique ECU software version. So if the SCU code gets updated from S01.05.0 to S01.06.00, the engineer must create a new versioned project.
You can't just update the files in the old one.
You absolutely cannot. That prevents the irreversible loss of historical calibration data. If we discover 2 months from now that a drivability issue existed in the older code but was fixed in a previous calibration, we have to be able to pull that exact versioned data set.
That makes the entire process auditable by default. Okay, let's switch to CANape, which is often used for more advanced analysis and automation. We have to talk about its scripting power.
Yeah, CANape's real strength is its CASL, the calculation and scripting language. This gives the engineer the power to define real-time virtual signals. And this is critical for complex hybrid systems where no single sensor can tell you the whole story.
Give me an example. What's that critical virtual signal total wheel torque for our cement truck?
Right, so that signal is impossible to measure directly with a sensor, but it's essential for diagnosing the hybrid transition. Using CASL, the engineer can calculate it in real time as
Sure.
engine torque plus motor torque gear ratio.
So you're summing the two power sources.
Exactly. And why is this so vital? If the engine compensates too quickly and the motor compensates too slowly during a shift, the individual torques might look fine on their own graph. But the sum, the total wheel torque, that will show you that the driver experienced a harsh spike or a shunt. Without that virtual signal, that spike is completely invisible to you.
So CASL is like a real-time diagnostic synthesis tool.
Yeah.
Can it also just automate the sheer drudgery of calibration work?
Absolutely. Think about mapping the e-motor's efficiency. That means you have to log data points across its entire speed and torque range. It's a massive, repetitive task.
Hours and hours on a dyno.
Or in a vehicle. A CASL script can control a dynamometer or command the vehicle to execute a test sequence automatically. It can say, scan the motor speed from 0 to 3,000 RPM, pause at every 100 RPM increment for 5 seconds, and record all the current voltage and efficiency data. This automation just removes hours of manual error-prone effort. It directly accelerates the debug loop.
So when all this data is being generated, the parameters, the logs, the scripts, we need a gatekeeper to ensure quality. The blueprint says that role belongs to CDM Studio.
Yes, CDM Studio, the calibration data manager, is the system that transforms tuning into accountable engineering. There's a truism here. Calibration without CDM is just randomly modifying data on the vehicle.
That's a strong statement.
It's true, though. CDM is mandatory for data governance. Its main uses are comparing calibration files, your DCMs or PRs, against baselines and generating formal audit reports.
So it sounds like it forces engineers to actually justify their work.
It does. When an engineer uploads a new calibration set, CDM automatically compares it against the previous version, and it highlights every single parameter that was changed. The engineer then has to supply an engineering rationale or a reason code for every single change.
I see.
That documentation becomes the official record of the team's intellectual property and its compliance history. It moves the conversation from, hey, why is this truck so slow, to show me the rationale for the change made to the torque limit map on May 15th.
Let's talk about the critical process of flashing the ECU, often called Pro-F. The stakes are really high in a 400-volt hybrid truck. What's the safety protocol here?
The pre-flash safety checklist is completely non-negotiable. Mandatory checks. The vehicle has to be totally immobilized, park brake engaged, wheels chalked. The high voltage system has to be safely disabled and disconnected. And critically, the current calibration data must be backed up before the flash even starts. You never overwrite data you haven't saved.
And the mentor's caution on verification is a strong reminder.
It is. Flashing without verification is more dangerous than flashing incorrectly. After the flash, the engineer has to verify the new software ID and the calibration CRC, the cyclic redundancy checksum. If that checksum doesn't match the expected signature, you have a corrupted flash and the vehicle is unsafe. A fundamental high-level functional test, a simple smoke test, has to follow immediately just to make sure the ECU woke up correctly.
You mentioned accelerating the iteration loop through something called partial flashing. Can you clarify how this speeds up the process from, say, minutes down to seconds?
Yeah, so in the rapid development cycle, the underlying software, that HEX file, it often stays constant while the calibration parameters, the maps and curves, change very frequently.
Right, you're just tuning.
Exactly. The calibration data lives in a specific, relatively small sector of the flash memory. Partial flashing lets the tool target and write only that specific calibration data sector, and it ignores the main operating system code. So instead of spending 5 minutes rewriting the entire ECU memory, you spend maybe 10 seconds rewriting just the parameter area. It drastically improves the efficiency of tuning.
Okay, we've built the discipline environment. Now we get to engage with the actual physics. Pillar 3 is core control, focusing on PID tuning. And we're not tuning some abstract digital filter here. We're tuning a massive rotating drum full of concrete.
And this is where we hit extreme nonlinearity. The PID loop for the cement drum speed control is notoriously difficult because the load is constantly changing. The slump, the water content, the temperature of the concrete, the dynamic mixing action, it all alters the friction and the inertia of the system.
So it's a high-inertia system that's operating at low speed.
Exactly, which makes it exceptionally unstable, particularly during that crucial startup phase.
So if the mass and the friction are always changing, the physics dictates that a single static set of PID parameters is just doomed to fail.
That is the engineering conclusion right there.
Yep.
This is not an object that can be handled by a single set of PID parameters. If you tune it for an empty drum, you'll get severe oscillation when it's full. If you tune for a full drum, the empty drum responds way too slowly. So our goal here is to shift this from, an iterative guessing game to a systematic, repeatable engineering method.
Okay, let's walk through this step response tuning SOP. Before we even touch the knobs, what's on the mandatory checklist?
3 things. 1, confirm you have clean, stable speed feedback signals logged at that necessary 1 millisecond raster rate. 2, ensure the motor torque command is not being artificially limited by any other control module. We need the PID to have full authority to drive the system, even into instability if we need it to.
And 3,
Set the integral, the I, and derivative, the D, gains to 0. We have to isolate the P term first.
okay, so the core principle of this whole process is, first, let the system oscillate, then stabilize it. We start by tuning P, the proportional gain.
Right. P determines responsiveness, how quickly the system reacts to an error, which is the difference between your target speed and your actual speed. We slowly increase P, usually in small steps, while we apply a step input and watch the speed waveform. We're looking for the critical point where the system enters a state of continuous, undamped oscillation.
That sounds counterintuitive. We're intentionally looking for instability.
We have to. We need to know the system's inherent limit. That critical P value, right where the oscillation first appears, that's the upper boundary. The actual working P value should then be set more conservatively, typically somewhere between 50% and 70% of that critical value. This ensures a fast response without being right on the edge of instability. P gives us the speed of reaction.
So once P is set, we address the persistent errors with I, the integral gain.
I-tuning is all about accuracy. Its fundamental purpose is to eliminate steady-state error, that tiny persistent offset between your target of 10 RPM and the actual 9.8 RPM you're getting, which is common when you're fighting the constant sticky friction of the concrete.
So you increase I slowly to close that gap. But you said there's a major risk here, integral windup.
A huge risk. Integral windup happens when the PID controller demands a torque that the E-motor physically can't deliver. Let's say it asks for 1,500 nm, but the motor's limit is 1,000 nm.
Okay.
The error persists, right? And the integral term just continues to accumulate that error until it becomes this massive, massive value. When the error eventually reverses, say the target speed drops, that massive accumulated I value causes the system to seriously overshoot or surge violently, especially on startup or during sudden load changes.
So the blueprint says what?
It makes it clear a robust anti-windup mechanism is mandatory in the SCU software to cap that accumulation.
So P gives us speed, I gives us precision, and finally D, the derivative term.
D determines stability and smoothness. It reacts to the rate of change of the error, so it provides a damping force to inhibit overshoot. However, D is by far the most volatile term. It acts like a high-pass filter, which means it amplifies high-frequency noise.
And in this EMI environment, you're going to have noise.
You will. If your speed feedback signal has any electrical jitter, the D term will amplify that noise into torque pulsations, making the drum rotation feel jerky. So the practical engineering advice here is critical. Avoid using D unless the feedback signal is strictly and robustly filtered. A noisy D term does way more harm than good, and often its value just needs to be set to 0 in these low-speed, high-inertia environments.
We can probably summarize the effects of all these terms with the mentor's mantra.
Yeah, it's a good one. P determines fast-slow, I determines accuracy, D determines how it looks. To reiterate the effects, P lowers rise time, but it increases overshoot. I eliminates that steady-state error, but it can dramatically increase the settling time. And D reduces overshoot and improves stability, but only if the signal quality allows it.
Okay, since we've established that a single PID set fails, Because the drum load is so nonlinear, the solution is to implement gain scheduling.
Correct. Gain scheduling basically implements a 2D PID map. We have to recognize that the physical object, the drum, acts like a radically different system when it's empty and operating at high speed versus when it's full of setting concrete and trying to start from zero. A single set of P, I, and D values just can't satisfy those completely different demands.
So how does the SCU use that map? What are the indices, the AXI, SPTS, for this control strategy?
The map is typically indexed by two variables. First, a measurement of the load. This could be estimated load derived from hydraulic pressure or a model that estimates the concrete weight.
What?
And second, the target speed of the drum. This map contains pre-validated PI and D values for every major operating zone, which allows the SCU to instantly switch to the appropriate control parameters whenever the operating environment changes.
And when the truck transitions from, say, low-speed mixing to high-speed unloading, the system is moving across those index points on the map. What's the danger during that transition?
The transition itself can cause a shock. If the SCU abruptly jumps from one high p-value to a different, much lower p-value as it crosses a boundary, the result is going to be a noticeable torque discontinuity, a sudden jerk in the drum's rotation.
So you need to smooth it out.
Yes. A crucial implementation note is the requirement for smooth parameter transition, or interpolation, when switching between points on the PID map. The control system has to blend the parameters seamlessly to avoid those shocks.
We've stabilized the drum control. Now we integrate this into the vehicle chassis and, the driver's experience. The focus shifts to drivability and taming the jerk during acceleration and deceleration.
Drivability is often the most subjective and challenging aspect of calibration, but the blueprint gives us a really precise engineering foundation. The perceived jerk, or that lurching sensation, it's almost never because of the maximum torque magnitude.
It's something else.
The engineering conclusion is definitive. It's caused by excessive torque change rate, DTDT.
So it's not the destination, it's the acceleration curve you take to get there.
Exactly. Drivability issues are declared to be 80% problems of the time axis, not the magnitude axis. A smooth 500 Newton-meter pull feels good. An instant, uncontrolled spike of 200 Newton-meters feels like a lurch. And this principle guides the entire pedal map strategy.
And since this truck spends its life maneuvering slowly on these really congested job sites, how should the pedal response be tailored for that?
The blueprint really stresses this unique operating environment. Drivers are often using very fine foot movements for precision. They're, using their toes, not their heels on a racetrack.
Right.
Therefore, the low pedal region, typically from 0 to 20% opening, it must be intentionally dull. The torque slope has to be shallow and less sensitive, which allows for that fine, predictable maneuvering without any accidental lurching.
And how do we control that critical DTDT across the entire torque envelope from low speed to high speed?
We use the core calibration parameters, torque ramp up and torque ramp down. These parameters are direct rate limiters, and they're calibrated in units like Newton meters per millisecond.
Enzymes.
Right. By setting these limits, maybe between 50 and 200 millimeters, you enforce a maximum rate of change for the total requested torque. This ensures that the driver experiences a smooth, predictable, and comfortable response every single time they modulate that accelerator.
Now we get to the very core of hybrid complexity, the torque fill strategy during mode switching. This sounds like the difference between a smooth transition and a really violent shunt.
This is the soul of the P2 parallel hybrid architecture. When the engine engages, there's a mechanical sequence. The clutch closes, the engine speed synchronizes, and then the engine slowly builds up stable combustion torque. Physics mandates that during this transition, there is a momentary power gap delivered to the wheels. We call it the torque hole.
And if the driver feels that gap, the truck feels like it's stalling or jerking backward.
Exactly. It's a terrible experience. The genius of the hybrid system, then, must be to use the e-motor's instantaneous response to completely mask that mechanical latency.
So the goal is seamlessness.
Complete seamlessness. The e-motor has to execute a precisely timed torque fill compensation pulse to ensure that the total torque provided to the wheels remains constant and equals the driver's demanded torque throughout that entire engine engagement process.
Let's break down the 3 calibration steps for this. This has to be flawless.
Okay, step 1, timing alignment. This is the most complex part. The motor's compensation pulse has to be precisely aligned with the clutch engagement and the onset of stable engine torque. The signals engineers need to be watching here are high-speed engine speed feedback and the motor torque command.
And if the timing is off by just a few milliseconds?
If the motor compensates too early, the driver feels an unwanted push. If it compensates too late, they feel the torque hole. It has to be perfect.
Okay, what's step 2?
Step 2, magnitude compensation. This is all about precision. We have to compensate for the gap only, not just add a fixed amount of torque. The motor's output has to be calculated dynamically to mirror the exact instantaneous amount of missing engine torque.
Right.
The blueprint's guiding quote here is, filling accurately is more important than filling excessively. If you overcompensate, you just replace the initial hole with an unwanted shove, which is just as bad for drivability.
And step 3 is the exit.
Step 3, the exit ramp. The motor's job is done once the engine is stable, but it can't just cut its power instantly. It has to exit the compensation phase with a controlled, gradual slope. If the motor abruptly drops its torque contribution, the driver feels a second negative jerk. So the motor's exit slope has to be specifically calibrated to be slower and more gradual than the engine's entry slope. This guarantees a gentle, smooth handover of the load back to the combustion engine.
Beyond highway driving, a cement truck spends a huge amount of its time operating at extremely low, precise speeds, especially on a construction site. This brings us to creep control.
Creep control is absolutely essential for predictability. It provides a predictable thrust below, say, 3 kilometers per hour without the driver needing to touch the accelerator. It mimics the feel of a classic automatic transmission where the vehicle just naturally rolls forward when you release the brake.
So what are the two opposing physical constraints that define the correct creep torque? It sounds like a delicate balance.
It is. The torque has to be sufficient to overcome the vehicle's static friction to make sure it reliably starts moving on a flat surface. That's the lower boundary.
And the upper.
The upper boundary is driver comfort. The torque has to be less than the acceptable limit upon brake release to prevent that sudden, uncomfortable lurch or jump. To achieve this, the blueprint advises using a dedicated, very finely tuned creep torque map that's completely separate from the main pedal map.
And finally, a really persistent low-speed issue, longitudinal shuffle. The truck can start oscillating back and forth at 2 to 5 hertz just due to driveline backlash. How does the hybrid system fix what is essentially a mechanical problem?
This is where the sheer speed of the e-motor becomes a mechanical solution. The advanced strategy is called active damping. The SCU constantly monitors the high-frequency speed fluctuations caused by that driveline backlash. It then calculates an inverted opposing counter-torque pulse. And since the e-motor has millisecond-level electrical response time, it applies that inverted pulse instantly to counteract the mechanical oscillation.
Wait, so the motor is acting as a virtual, incredibly fast electronic shock absorber?
Precisely. It's reading the onset of that mechanical spring mass effect, and it's canceling it out before the oscillation can grow large enough for the driver to even feel it. The e-motor compensates for the mechanical sloppiness by applying a nearly instantaneous electrical counterforce.
We've tuned the system for performance, for comfort. Now we have to transform this validated data set into a mass production asset. This brings us to the fifth and final pillar, functional safety and data maturity.
This is the non-negotiable gateway to the factory. Performance is completely irrelevant if the data governance is poor. The calibration data set has to be treated as a control asset. To do that, we use the VDA MLA, the Maturity Level Assurance Model for calibration data governance.
Okay, let's walk through how this model structures a progression of data trust, starting at the lowest level.
We start at ML0, DRFT. This is initial tuning. It's strictly for lab use, and it might be, very unstable. Next up is ML1, BDA. Here, basic functionality is verified, which allows for use in closed area testing.
Okay.
The key gate is ML2, PRB-CAL. This data has undergone full environmental and durability testing, high and low temperatures, extreme load cycles, and it's now ready for public road tests. Crucially, ML2 data must have passed 100% of the formal ISO 26262 fault injection tests.
And the final, factory-ready state.
That's ML3, release SOP. This is the final frozen version. All parameters are locked, verified, digitally signed, and ready for mass production serialization. This whole structure ensures that risk is systematically reduced as the data progresses toward its release.
And this rigor is all driven by ISO 26262, functional safety. Calibration parameters aren't just inert numbers. They are safety-critical components.
Absolutely. Parameters like max drive torque limit or the maximum allowed drum speed, these are classified as ASIL-C or even D Automotive safety integrity level. If these are incorrectly set, they could lead to loss of control or a major component failure. So we implement multiple redundant layers of protection.
Starting with layer 1, safety that's enforced by the A2L contract itself.
Right. The A2L file is used to restrain the calibration engineer. We use the readily attribute to prevent modification of certain critical items. But most importantly, we define strict lower limit and upper limit constraints right in the A2L definition. This prevents the engineer, even if they make a mistake in the tool's GUI, from setting the maximum torque limit to an unsafe value that's outside the pre-validated physical bounds.
Okay, and layer 2 addresses the communication highway itself.
This is mandatory E2E, or end-to-end, protection on the XCP communication protocol. Since the tool is writing directly to the ECU's memory, we have to ensure the data gets there intact. E2E protection involves adding a sequence counter to every XCP data packet to detect if any frame was lost or arrived out of order, and it adds a CRC checksum to detect data corruption during transmission.
And the third layer provides security upon power-up, independent of any external communication.
The ECU bootloader provides the final defense. On every single vehicle power-up, the bootloader must perform a mandatory full-area CRC checksum verification of the entire calibration data sector. If the calculated checksum doesn't match the stored validated signature, meaning the data has been corrupted, tampered with, or flashed incorrectly, the ECU has to immediately recognize that data integrity failure and enter a safe limp home state.
And the ultimate proof that these safety layers actually work is the fault injection testing. This is where engineers intentionally try to break the system.
This is the critical ISO 26262 verification step. Engineers will actively use tools to simulate sensor failures. For example, they might override the brake pedal sensor signal to 0 while simultaneously simulating the accelerator pedal at 100%.
An impossible state.
An impossible state. And they then verify that the SCU's internal safety monitors detect this and cut torque within the required fault-tolerant time interval, or FTTI.
FTTI is the time the system has to go safe before a catastrophic event can occur.
Yes, and it's often measured in milliseconds. This verification process proves, under audit, that the safety mechanism works exactly as designed, independent of the primary control strategies. This is what moves the dataset to ML2 maturity.
So once that verification is complete, we can finalize the data freeze and move to ML3 release.
Right. The data freeze requires generating a formal diff report, usually with CDM Studio, comparing the final calibration against the immediate prior version. Every single parameter change has to be justified with that mandatory engineering rationale, or reason code. That report is then formally reviewed cross-functionally by the safety team, the hardware team, the software teams.
And what's the final output package that gets archived?
The final data and code are merged into the final .hex file. For ACEL compliance and traceability, that file is then digitally signed using a private key to confirm its authenticity and origin. And the entire package, the A2L, the HEX, configuration files, all the review reports, is archived in the Product Lifecycle Management, or PLM, system. That marks the end of the disciplined, repeatable process.
The blueprint masterfully translates all of this theory into structured, actionable checklists to make sure no critical scenario is missed. We need to categorize these tests based on where they actually occur.
And these structured checklists are what ensure we move from theoretical stability to real-world robustness in a systematic way. It guarantees we cover the entire operational envelope.
Okay, let's start with static calibration in the Dyno Lab. What's the focus when the truck isn't even moving?
The lab focus is all on the electrical subsystems and the initial control loop linearity. Key items include verifying the current loop linearity, confirming that the motor's actual torque output precisely matches the commanded torque input.
Okay.
We also map and tune the dead zone compensation for low-speed motor rotation to make sure the motor can start smoothly without sticking. And crucially, we perform the initial gain scheduling validation, checking that the control waveform switches smoothly between a simulated empty load and the simulated full load scenario without any oscillation.
Next, we move the truck to the dynamic calibration at the proving ground. Here, we're testing the entire driveline under load.
The focus here shifts entirely to dynamic drivability and validating those safety functions under real-world conditions. Key items include verifying full throttle acceleration, or WOT smoothness. We're specifically looking for any transient torque holes or jerks during the mandated engine intervention.
Right.
We verify hill start performance to ensure the creep and torque fill timings are flawless under maximum static load. And finally, we perform emergency braking tests to trigger the ABS and confirm that the torque shutdown logic is immediate and effective, preventing any unintended drive during a safety event.
Finally, the ultimate test of durability and system adaptability, environmental calibration in extreme conditions.
This tests the robustness of the system when external factors are actively trying to degrade performance. A key item here is high-temperature derating curve verification. If the power electronics overheat, the SCU has to smoothly reduce motor power. We have to confirm that the PID parameters adapt to that reduced power capability without introducing oscillation or overshoot. The system has to remain stable even when it's running at half capacity due to thermal limits.
And low temperature conditions.
Low temperature and high humidity testing ensures stability on low adhesion surfaces. The stability of the creep control, especially on slick, icy ground, is vital for site safety. The final goal here is cross-condition verification, running the truck continuously from empty to full load across all thermal extremes, ensuring the PID map and the hybrid strategies adapt robustly and maintain stability across the entire operational envelope. That's what proves the system is ready for the factory.
This deep dive into the SCU calibration blueprint for the P2 hybrid cement mixer truck, it's been an incredible journey. It really defines what it takes to transform a complex, high-voltage mechanical system into a safe, efficient vehicle. We established the necessity of high-speed communication with CAN FD and XCP. We enforced the disciplined use of tools like INCA and the data integrity of CDM, and we tackled the core physics of nonlinear PID control using gain scheduling. We then ensured a comfortable, predictable drive through accurate torque fill and underpinned the entire process with the non-negotiable safety standards of ISO 26262.
We've really shown that calibration is no longer an unpredictable art. It's a disciplined, a repeatable, and an auditable engineering process. But the ultimate measure of success for this complex system, it ties back directly to its fundamental purpose: reliability. For a cement mixer, the single most catastrophic, mission-critical failure is not a roadside breakdown, it's the hardened batch scenario.
Concrete solidifying inside the drum. An engineering disaster that requires, what, dynamite or days of hammering to solve?
Exactly, a hugely costly and dangerous failure. Therefore, the final overarching engineering commitment defined by this blueprint is task reliability. The SCU calibration must ensure that the battery state of charge, the SOC, always reserves enough power, typically greater than 40%, to ensure it can always perform the crucial unload function using the ePTO system, even if the main engine fails. Preserving that electrical capacity is intrinsically linked to functional safety and, frankly, operational profitability.
That operational constraint is the perfect point to end on. It defines success not by speed or power, but by the ability to guarantee the core function. Earlier, we noted that the source material defines the control strategy access points, the ASI-SPPS, as not just mathematical coordinates, but the application boundaries of the control strategy.
Right, it's the definition of the control domain.
So if PID tuning and gain scheduling are fundamentally about defining these critical boundaries, when to use a high gain, when to use a low gain, consider this for yourself. Where in your own domain, whether that's professional projects, personal finance, or wellness, might you currently be operating without a clearly defined boundary? And what hidden risks or unexpected oscillations are you incurring as a result of operating in that necessary but currently undefined territory?